I would like to introduce Antonis Carrington, who will be presenting Securing the Internal Control Plane with Standards and OSS. Antonis is a researcher at Cisco, joining us from Zurich in Switzerland, where it's a little bit past midnight. I don't know who wrote that. This is Antonis' first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Antonis.
I hope I won't keep you here for very long. I have a quick presentation with maybe an interesting idea to share with you. It's almost midnight here, so it's not in my benefit to stay too late here either. I think you can see the slides already, so we are ready to begin. And let's talk very briefly about the internet. I'm sure you've heard of that and you are familiar with it. It's basically a bunch of autonomous systems that interconnect with each other and form some sorts of topology and path to get traffic from one place to the other. The thing that I would like to specifically focus on today is these interconnections, these relationships between the autonomous systems that are, of course, eBGP sessions. So these are eBGP sessions. They're ripe for problems because if someone misconfigures their router, maybe there is a typo, some mistake that they honestly make, then this can create route leaks. Maybe they did a typo typing a prefix in, and they cause a hijack of the traffic. Or some people may try to do malicious things in these interconnections between ASs. For example, they may want to hack some, cryptocurrency exchange or something, or a bank, and they are performing an intentional hijack. But also all of these networks that have other priorities and are not always running state-of-the-art filters and validations in their networks. Maybe they haven't deployed RPKI, origin validation. Maybe they haven't signed their ROAS. We're seeing these problems on the internet every day as operators. And there are some playbooks that most people are probably familiar with in this room on how to deal with that, how to deal with a BGP session to someone else that you don't know or trust necessarily, which includes doing RPKI validation and dropping invalid prefixes from origins that should not be there, doing IRR filtering, either RPSL or even just route objects, and generating route maps and prefix lists to automatically configure all of your machines from. There's also a known list of autonomous systems and of IP addresses that should not hopefully appear on the internet, and these are updated every now and then. And there are also prefixes that are, too big or too small to appear on a regular external BGP session. So this is something that most networks are hopefully already doing, and it's a fairly known playbook, and it has served us well for all these years. And if you do everything correctly and you have a route, you can be fairly sure, or as sure as we can be in these days, that a certain route from a certain origin should actually have traffic sent to it from that BGP session. And it works. It's the state of the art right now. It's constantly being improved, but the internet is not broken too many times a day, so it should be okay. But I was thinking that, we have the internet here, which is a collection of ASs with eBGP between them. I've also seen enterprise networks that have a similar topology. Instead of public ASs within their own AS or within their enterprise network, they have private ASs in each location, and they interconnect with eBGP. Whether this is something that's smart or not, it's not up to me to judge, but it is a fairly common architecture that can be seen. And in some enterprise networks, they may have, a data center somewhere, and every rack can have its own autonomous system, or they may have branches all over a country, and every branch may have its own AS. And of course, each AS has its own IP addresses. Let's say it has a Wi-Fi VLAN for employees, and in the data center, there is some production VLAN with servers that have to be reached to perform whatever enterprises are doing these days. I've also seen it in some provider networks, usually smaller networks. So it's something that's a general practice that can be spotted in the wild. And for this network, if you look at that, we kind of have the same topology as the internet. We have a bunch of edges, and they interconnect with each other. And they have the same edges as you would on a regular internet. And usually when these networks are being built and developed organically, all of these connections are trusted, because on the internet it's some other company, maybe in a different country, operating on a different compliance regime. But within your own company, probably you can trust everything, so all of your routers are trusted. But this presentation is trying to raise the question of should they be, or are they all trusted? Because in an ideal world, you set up everything at the same time, you configured it, you're filtering everything properly. But in a real enterprise network with mergers, acquisitions, that's not always the case. So you have the same problems that could exist on the internet. Like maybe you misconfigure a filter and you send more routes, or you transit, let's say, your traffic through a branch. That's not very common. Or you do a typo in an internal prefix, you advertise something, and you cause an outage for someone else. So any problem that exists on the internet, in theory, you can cause it to your internal network, and it's not necessarily a colleague or another department. Maybe you yourself, like you legitimately made an error either in your automation or when you were SSHing into a machine and configuring it. And unfortunately, in internal networks, they may be more trusted and you may have full control over everything, but there's no playbook on what's going on. There's no IRR, no RPKI. You don't know what valid means. Like, if you think about it, if you belong in this category of networks, can you tell me right now which prefixes should and which prefixes should not appear? And which ASs should or should not appear? And every time a new AS or a prefix is added, let's say from 10/8, can you guarantee that this is being propagated to every prefix list, every route map that you have anywhere in your network? And the answer is probably not, especially if it's a network with multiple generations of software, hardware configuration. If you've done a lot of acquisitions, it gets meshier as you try to build connectivity across the entire enterprise or service provider network. So it's not only about security. I would say there is an argument about reliability here as well. Like, if there's a critical machine somewhere and someone with a typo causes an outage because they hijack this prefix internally and they're sending the traffic to the wrong place for half of your network, this could mean that your company cannot operate as effectively as it could. So does that mean we need to start validating internal routes now? And this was the question that I said to answer. And it may sound as an overkill, but let's talk about it. Let's see whether that makes sense. I asked some companies that told me they have this problem, what do you do over the past few years? And the most common response is we do nothing. We accept that there is a risk, and it's fine. Like, we'll find a solution. If something breaks, we'll troubleshoot it. We'll get there. And the more technical solution, the second most common one, was that, well, we have a bunch of prefix lists of what we expect behind every BGP session, either in terms of ASs or prefixes. And usually, in most of them, even if they had automation, this list was mostly handwritten. Like, you set up a router once, you configure the prefixes, then if you extend your network, you don't go back and update everything. And this can cause subtle problems, like maybe you have a filter that allows traffic one way, but you drop the prefix the other way, so the traffic cannot return to the original destination. And these things, because they happen internally, they're very difficult to troubleshoot, from what I've heard. And they can cause packet loss, they can cause difficult scenarios for NOCs of enterprises. So the question then is this a problem worth solving? Is this something that should be prioritized high enough or at all? Or should we try to find a solution? And based on this anecdotal evidence, at least, like me talking to people over the past 4 or 5 years, it turns out that this can cost money. It is something that complicated networks have. And these outages can be expensive. It's very difficult to find the root cause and therefore recover quickly from them. So I would say that for some networks, probably very few of them, not most of them, it's probably something worth looking into. What do you do for your internal network and control plane? Not security, but also reliability. So in order to try to test all of that, I created a personal AS, 4601. And it's a network that I run on my own free time. Like, everything is a hobby here. So it's not as important. I can try more crazy things that would be more insane to try in a production enterprise network. And I can learn from that, and I can share this knowledge and all of this experience with everyone in talks like this one. So let's dive a little bit deeper into how I've set up this network to see how it works. So first of all, I don't have any iBGP route reflectors OSPF. 100% of this network is built on eBGP. Every router has its own AS. The only difference with the previous design is that I'm using BGP confederations. So every router appears outside the AS as 4601, and internally with everyone else, it has regular BGP and has the same process as if it would on the internet. And it has its own routing table. It makes its own independent decisions. There's no centralized authority. It's a distributed and more resilient network by design. There is some collaboration with BGP large communities, like I prefer IXPs over transit. There is all of that built in, but it's not centralized logic that exists somewhere. Every router still has to make its own choices. I have around 20 IP routers with full tables. So it's not a huge network, not a large network, but it's large enough where you can see what works and what doesn't and what breaks first. And because it's a hobby network, I used to buy whatever hardware I could find on various, second-hand markets. But I am trying to standardize now running Debian and Bear2 for control plane to make automation easier. So this is a network that I've tried to use to answer this question. And the architecture, like the topology, is similar to what we described before. The only difference is BGP confederations. Even if you don't use them, even if you don't know what they are, the rest of the talk should apply just fine. If you do, they probably make your life easier. So we have a public playbook that we've seen earlier that has a bunch of things that we are doing for all of our external relationships. And the problem is that, these RPKI, IRR, all of that, it's kind of useless. There's no IRR for your own enterprise network. You don't necessarily know what is a bogon and what isn't. You have all these sorts of exceptions, more exceptions than rules typically, that you have to deal with. But I was thinking, like, this playbook came from decades of operational experience. Let's try to reuse it. Let's try to reuse as much of that as possible. Let's not throw it away and start from scratch, and see where that gets us. And this is the simplified version of the playbook that I came up with, and I wanted to try. Basically, I understand IRR is being replaced slowly by RPKI, so let's just jump straight to RPKI. Let's use RPKI and ensure that our network internally has the same guarantees as the internet externally as well. And of course, because RPKI was designed for the internet, the public one, you can't really use it that easily in your own network, which means that you have to run a private hierarchy. The same with the web PKI and TLS and web servers. Anyone can run their own internal version of RPKI. It is a bit complicated. We'll get into that later. But in theory, it is something that is possible, and it simplifies everything a lot. And because in this network, you control everything, you can sign ROAs for all of your prefixes, not some of them. So in theory, you can also drop unknowns. You can take it a step further, not just invalid routes, which, again, caveats that we'll get into later. It's not as easy, of course. As long as you have a single source of truth, like anywhere in your network, you can tell me which prefix should correspond to which internal AS. In theory, RPKI should already be a very good step forward. So in my network, this is an example of what my ROAS look like. There is, let's say, a /31.2 link that originates from this internal prefix. There's a /29 VLAN somewhere, originates from this other internal AS. IPv4, IPv6 doesn't really matter. As long as you can create this table here of prefix to origin, you should be good. The first thing I noticed was that my filters on BERT were actually very, very simple. I don't know if you can read this, but effectively, the only thing that I have to check is if the network is an IGP network, which means it's my own IP addresses, or RFC 1918 for IPv4, I check if it's valid. If the prefix is valid, I can use it. If it's invalid or maybe unknown, I can safely drop it, because 100% of my internal prefixes are RPKI signed within my hierarchy. And this was the initial idea. I said, okay, let's try that. Like, it looks simple on paper. Maybe, like, it's a lot of details will come out later, but let's try this. So how did I do this? And I started many years ago, where it was more difficult. I had to write all of this code myself. But lately, NLNet Labs, that I'm sure you know, a non-profit writing open source critical software from the Netherlands, has created Krill. And Krill you can use for basically delegated RPKI. Some of you may be doing that. But you can also use it for root CAs, not just sub CAs that are delegated from ARIN or RIPE or whatever it is. It supports HSM-backed private keys if you require some sort of private key and key management protection. And you can create whatever hierarchy you want internally. So it seems to simplify a lot of things, and it has a very useful API. The next thing is that you have to add your data. Like, your existing network doesn't have RPKI, the internal one. You have to find a way to import everything. Like, if you use Excel, I'm sorry to hear that, but of course it's very common. I'm not judging anyone. I happened to be using Netbox, so it was very easy. Netbox has an API. Krill has an API, or the code that I wrote also had one. So I was able to import all of the prefix to AS mappings, the internal ones, into Krill. As long as you have this map, you can write a script, find a way to do this. And the next thing is to, of course, keep it in sync. So if you have a single source of truth, you need to make sure any changes to Netbox, for example, they appear on Krill as well. As a benefit here, because you're validating RPKI, if you forget to do this or this breaks, your network, like any changes to your network, will not work. So I think that's a feature, not a bug. And you'll know that it's broken and you'll have to fix it. So be careful about that. But yes, you get the idea. So the final step is getting the data into the routers. If you do RPKI on the public internet, you probably use Routinator or RPKI client. So this part is basically the same. You have a different instance of Routinator or RPKI client. It's not the same as the public one. And you just have your internal RPKI hierarchy being served to all of your machines through that. And the same architecture you use for your existing routers, you can use it for this too. So this should be the easiest of these steps. So I did all of that. I got the internal data into my routers, and it was done, right? Well, not really. This is, I think, the most valuable part of this presentation, and this is why I wanted this to be kind of a brainstorming discussion type of thing, and it's not an authoritative presentation of here's how it's done and here's what you should be doing. I wanted to share the lessons that I've learned by operating this in a production network for a few years now. So let's see what the problems and the issues I run into are and how we can get around them. So first of all, if you have two RPKI sources, like the public routinator for the internet, the private one, not every BGP implementation supports it. I was very lucky to use Bird that does this. You can have different tables, one for internal, one for external validation, but not all of the software do it. I think that in theory you can merge this into a single routinator, and it would probably work, depends on how you design your network. For my case, because I was using Bird, it was actually very easy. I have a different table that I'm checking. So that was a solved problem. If you use FRR or maybe some of the hardware routers, it should probably be something worth checking before you do anything like that. The other problem was BGP confederations. It's a bit difficult, like they're not completely 100% in feature parity with regular AS paths. So for example, in Bird, there's no way of telling if you see in the filters, if you see confederation 6500 or if you see public AS 6500. So there was a bit of an issue there of getting things to filter properly. I think that if you use confederations, that's something that you've already dealt with and you have probably solved. And this was the case for me as well. If you don't use confederations, you have simple, regular old eBGP with private ASs, none of that should be a concern to you. So, you know, like simplicity pays off. So that's probably not a concern. The next thing was that RPKI does not protect you from all of the attacks today, at least. RPKI ensures that the origin is this prefix is basically tied to an origin. It does not check anything in terms of the paths. So some forms of hijacks, some forms of misconfigurations are not being caught by RPKI. There is ASPA, It's being finalized for the past 5 or 6 years or something. So maybe one day it will be standardized and you can use it. A lot of software started supporting it already, and it's going to go out by the end of 2026 in RIRs as well. So that's good news. But BERT, for example, supports it. The only problem is that ASPA was designed for the public internet. You need to be a little bit smart with how you set up your network. If it doesn't have, a tiered topology, if it's more distributed or like a mesh network, you may have trouble expressing all of these relationships into ASPA. And of course, that means that you also need to move all of your edges of your graph to Krill or to whatever RPKI software you're using. So I don't know what you use to represent this. Like some companies I spoke with, they use Visio. So as long as you can convert it to YAML or something like that, it should be fine. What I am doing before ASPA, the implementation, the rollout of ASPA, is I filter, basically added another section to the filter of which ISs I expect behind this BGP session. So it's not like it's a good first step, but it's not the same as ASPA. But even if you just do a regular RPKI, you're already solving most of the problems. Finally, something I learned the hard way is that because the RPKI, the routinator, let's say, is living in a prefix, and you don't accept valid prefixes, if it restarts, if something happens, the problem is that this will be unknown. And I told you earlier that perhaps you can drop unknowns. So I had this issue where something restarted, like a power outage in a data center, and a router could never come up. If you have an out-of-band network to run your routinator in, that's great. If not, what I did in my case was that I have a special prefix that hosts all of the software like Krill and Routinator, and this prefix is okay to be unknown. All of the other prefixes, they have to be valid. This one is okay to be unknown, but with local pref, I prefer a valid over an unknown version route of this prefix. And technically, all of the authentication happens at the application layer, so it's probably fine. It's not the end of the world. And in my instance, the routinator lives very close to every router, sometimes in the same machine as well. So this was also okay.
Hey, Anton,
I guess I'm not the only person.
can you hear me?
Design. Yes.
Sorry to cut you off. We're out of time, so it would be great if you can wrap up and we can do questions.
Okay. This was my final slide, so I'm happy to take questions now.
Yeah, so sorry for that.
No, it's okay.
Do we have any questions online? Nothing. All right. Thank you, Anton.
Enjoy. Here.